Okay, the moment you've all been waiting for. More AP Stats questions. Woo! So, a survey will be conducted to examine the educational level of adult heads of households in the United States. Each respondent in the survey will be placed into one of the following two categories: does not have a high school diploma and has a high school diploma. This survey will be conducted using a telephone interview. Random digit dialing will be used to select the sample. A says, for this survey, state one potential source of bias and describe how it might affect the estimate of the proportion of adult heads of households in the United States who do not have a high school diploma. Okay, so lots of correct answers could show up here. And it's important to note this is from 2005. Far fewer people have landlines and far fewer people answer calls from unknown numbers or can even tell that it's an unknown number. Way back in prehistoric times, you just had this big plastic thing on the wall that would ring and it had no way of knowing who was on the line. And sometimes it was people doing surveys and you'd pick it up and it was grandma or someone doing a survey. And sometimes you did the surveys. So that really doesn't happen much anymore. We don't do as much of that. So the bias now might be more pronounced than back then. So one potential source of bias, you could get non-response bias. Bias if many people decline to answer. And people without a high school diploma may decline at different rates. A different rate than those with. Okay, so lots of potential issues. B, a pilot survey indicated that about 22% of the population of adult heads of household do not have a high school diploma. Using this information, how many respondents should be obtained? So what sample size do we need? If the goal of this survey is to estimate the proportion of the population who do not have a high school diploma to within 3% with 95% confidence, and justify your answer. Justify your answer, show your work. So the margin of error is 3%. So we're going to say margin of error is equal to the critical value, the Z star, times the standard error of your sample. So we know a lot of those pieces, but we don't know the N. We don't know the sample size. The margin of error we're looking for is 0.03 or less. I'm just going to use an equal sign and set 0.03 as my boundary, and then we'll get to ensuring that it's or less in a moment. With the Z star, for 95% confidence, that is 1.96. We use that a lot. Hopefully you'll just remember it. Lastly, standard error. So that is going to be our proportion. So 0.22, that's 22%, times 1 minus our proportion, all over our sample size, which is what we don't know. So we're going to use a variable because that's what we do when we don't know. Now it's just algebra. Divide both sides by 1.96. And popping that into the calculator, 0.03 divided by 1.96. It's about 0.0153. I'm rounding it for my writing. I'm leaving it be in my calculator so that I can continue using that number with all the decimals without rounding. All right. So then I'm left with 0.22 times 0.78 all over n. To undo this radical, I'm going to do the inverse operation, which is squaring. So in my calculator, I'm just going to hit the squared button. And I get 2.34 times 10 to the negative 4. So when it has that little e negative 4, that's scientific notation. And 0.22 times 0.78 is 0.1716 over n. Now, I need to isolate my n. If you don't already know exactly how to do this, just write out your algebra every time. You're going to multiply by n on both sides. These cancel out. Then we get 2.34 times 10 to the negative 4th n equals 0.1716. And then we're going to divide both sides by 2.34 times 10 to the negative 4th. And again, I've actually left these numbers in my calculator, so I'm not using the rounded versions when I'm actually putting it in my calculator. I'm going to wait and round at the very end. So I get here that n is equal to 732.465, but we don't have 0.465 of a person. So I'm going to say sample size should be at least 733 to ensure margin of error is no more than 0.03 at 95% confidence. So this is all about calculating the sample size given a proportion and a confidence interval. We didn't use 0.5 here because we had a percent that we thought it might be. You would only use 0.5 as your proportion if you really didn't know or you wanted to be like super conservative. All right. Last but not least, since education is largely the responsibility of each state, the agency wants to be sure that estimates are available for each state as well as for the nation. Identify a sampling method that will achieve this additional goal and briefly describe a way to select the survey sample using this method. Okay, I'm just going to get this out of the way for a second. Sound effects are important. It's what they teach you in teacher school, sound effects. Okay, so for C. In this case, I would use stratified random sampling with states as, oh, hi, cat, strata. Basically, this would allow you to get a reasonable survey from each state, be able to say information about the states themselves, as well as combining it for the nation as a whole. You should probably say more to part C. It's not really the focus of what we're getting at right now, so I'm going to move on. Alrighty. Number 3. For many years, the medically accepted practice of giving aid to a person experiencing a heart attack was to have the person who placed the emergency call administer chest compressions, CC, plus standard mouth-to-mouth resuscitation, MMR, to the heart attack patient until the emergency response team arrived. However, some research believed that chest compressions alone would be a more effective approach. In the 1990s, a study was conducted in Seattle in which 518 cases were randomly assigned to treatments. 278 to chest compressions plus standard mouth-to-mouth resuscitation, and 240 to chest compressions alone. A total of 64 patients survived the heart attack, 29 in the group receiving chest compressions plus mouth-to-mouth, and 35 in the group receiving chest compressions alone. A test of significance was conducted on the following hypotheses. The null is that the survival rates for the two treatments are equal, and the alternative is the treatment that uses chest compressions alone produces a higher survival rate. So I'm going to say that P for chest compressions is greater than the proportion for chest compressions and MMR. And then the null symbolically would be that they are equal. Like. Okay. This test resulted in a p-value of 0.0761. Interpret what this p-value means in the context of this study. So I like this question because this is a really good review of what a p-value is. P-values are conditional probabilities. So we start with if the null hypothesis is true, if the survival rates for chest compressions is the, if I'm going to use the survival rates for chest compressions are, the grammar's killing me here. Survival rate for chest compressions is equal to the survival rate for chest compressions plus mouth to mouth. The probability of getting a difference as big or bigger than we got in this sample is 0.0761 or about 7.6%. Okay. It's a mouthful, but basically, if this is true, this is the chance of getting what we got. Okay. B. Based on this p-value and study design, what conclusion should be drawn in the context of this study? Use a significance level of 0.05. And so this is our classic hypothesis test conclusion. You didn't have to do all the parts. You do have to do the conclusion. Same as always. Because the p-value of 0.0761 is greater than the significance level of alpha equals 0.05, we fail to reject the null hypothesis. There is not convincing evidence that the survival rate for CC alone is greater than that of CC plus MMR. And so again, that is greater than because this is what it was. So this is basically our alternative hypothesis. That's always that second part, that second sentence. And then because it's greater than, we fail to reject the null. There is not convincing evidence. Things always go together. Okay, part C, and this is a good little review of errors. Based on your conclusion in part B, which type of error, type 1 or type 2, could have been made? What is one potential consequence of this error? Anytime you are asked about error, I want you to draw the error table. It's like an area model, but an error model. So in this case, we'd have H naught is true. And in this case, we have H naught is false. Here we have reject the null because P is less than alpha. And here we'd have fail to reject the null because P is greater than alpha. Notice, we accept nothing. Okay. So if the null hypothesis is true and we reject it, that is a type 1 error. If the null hypothesis is false, but we fail to reject it, just get a weird little edge case there, that is a type 2 error. So in this case, we failed to reject the null hypothesis. So there's only one type of error that we can make, because there's only one type of error that you can make if you fail to reject the null hypothesis, and that's a type 2 error. So for the first part, based on my conclusion in part B, a type 2 error could have been made. A potential consequence of this is that chest compressions plus MMR, plus mouth-to-mouth resuscitation, could continue to be taught as the standard of care when chest compressions alone actually produce a higher survival rate. Okay. Cool. Last but not least for this little snippet, based on a random sample of 800 adults in the United States, a journalist reports that 70% of adults in the US are in favor of decreasing the voting age to 16. If the reported percent has a margin of error of 3.77 percentage points, what is the level of confidence? So this is something a little bit different than what we've done in class, but it's got the same basic principle. You set up the margin of error and you solve for the unknown. In this case, we're going to be solving for that critical value. So once more, margin of error is equal to the critical value times the standard error of the sample. Our margin of error is 3.77%, which as a decimal is 0.0377. Be very careful not to make that 3.77. Okay. We don't know our z-score. We don't know our critical value. We do know our standard error in this case. It's going to be the square root of 0.7 times 1 minus 0.7 all over 800. And again, these standard error formulas are just on the back of your formula sheet, second page of the formula sheet. So I'm just going to divide both sides by this whole chunk. And I'm going to be a little bit sneaky here and duplicate that. When I do that, I get, so 0.0377 divided by the square root of 0.7 times 0.3 all over 800. And I get 2.33 is equal to my z star. Now, a critical value is essentially just a z-score that's giving you a specific percent in between. If you do that z-score below the mean and that z-score above the mean. So what we want to know is if the critical value ended up as 2.33 on our normal curve, here's the mean. We have a z-score of negative 2.33 down here and positive 2.33 here. And we want to know what that area is. That's going to give us our level of confidence. How do we find the area between 2 points on our normal curve? That's right, normal CDF. If you're not having nightmares about normal CDF by the end of this year, I've not done a good enough job with it. So negative 2.33 is going to be our lower bound because we want to go from here to there, which means positive 2.33 is going to be our upper bound. Because these Z stars are standardized values, these are standardized. We're going to use a mean as 0 and a standard deviation as 1. When you pop that into your normal CDF, you're going to get negative 2.33, positive 2.3301, and we get 0.9802. So that's good enough to say this is 98% confidence. So that's our level of confidence. It's just using z-scores backwards. Now, if the journalist wants a margin of error of no more than 2.5 percentage points while maintaining the same level of confidence from part A, and we can assume that the 70% is maintaining, what is the smallest sample size that the journalist could use? Now we have to do this again, but we don't know that. So again, solving for sample size. You can thank one of your friends for asking for a lot of calculate the sample size problems. I think it's good. We now know our critical value is 2.33 for this level of confidence. And our standard error is 0.7 times 0.3, just 1 minus 0.7, all over n. Just like we did before. I'm going to divide both sides by 2.33, 0.025 divided by 3, and we get 0.01073 equals root of 0.21 over n, square both sides to undo the square root. And we get 1.15 times 10 to the negative 4th equals 0.21 over n. I know that this n and this number are going to switch spots, so I'm going to say n equals 0.21 over 1.15 times 10 to the negative 4th. Divided by second answer. And n should be 1824.11, but we don't want 0.11 of a person. So we should say 1,825 people is smallest sample size. All right. I hope that was helpful. I'll be back for the next part in a moment. Oh, I should have stopped.